There you go.
Thank you. Well, good morning, everyone, and welcome to Orton's online course. Um, my name is Joseph Hominy. I'm with Orton. I'll be doing the lectures. You can email me with questions. You can interrupt me with questions. Your course, you can bug me as much as you want. You'll also notice that there are two people from the American Ceramic Society, Michelle Martin and Greg Geiger. They'll be monitoring these lectures. They also did all the correspondence, so you probably got the emails from them. So this course is the third course in this second certificate, and it's on thermal shock and basically how to design materials to be thermal shock resistant. So I've shown here some different R parameters that we'll derive later on in this course. And all of these R parameters describe thermal shock behavior. And if you look at these parameters, you'll see an E, that's elastic modulus. An A is thermal expansion. K is thermal conductivity. The sigma terms are the fracture strength terms. And then there's also a gamma in here, a fracture surface energy. So these thermal and mechanical properties control these R parameters, which are directly involved in the thermal shock behavior. So the first 6 lectures are on these properties. So we'll do elasticity today, and then we'll do thermal expansion, thermal conductivity, fracture strength, and then there's 2 lectures on thermal shock, deriving the R parameters, and that'll include the fracture surface energies to initiate crack movement and to propagate a crack. So when we discuss these properties, we'll look at what affects the microstructures, and that controls the property. So in some cases, you want a low elastic modulus. In some cases, you want a high modulus. Some cases, you want a low strength. Some cases, you want a high strength. So we'll look and see how the microstructure affects these properties so we can control the properties and then control the R values and control the thermal shock behavior. So when we finish the theory, we'll go over all these different refractory systems: alumina silica, basic refractories, zirconia-based refractories, non-oxides like carbon, silicon carbide, and silicon nitride, the carbon matrix composites, and then monolithics. So what I put together here are a series of case studies. We'll look at the different materials, how they're tested, because there's a variety of thermal shock test methods. We'll look at the microstructures that improve thermal shock resistance, and then the thermal shock behavior. So the second part of the course is all about what's been done on these different refractory systems to improve their thermal shock behavior. So today we'll do elasticity. I'm not sure if we'll get through all of it. It's a pretty long lecture, but we'll define normal stresses and strain, shear stresses and shear strains, the Poisson's ratio. We'll look at stored elastic strain energy because that's the driving force for fracture. And I'll mention the state of stress, elastic relationships for isotropic bodies, and refractories are considered to be isotropic. General trends in the elastic properties of materials, what controls the properties, some examples of refractories, and then the effect of porosity, microcracks, and temperature on the elastic behavior, and then finally a brief section on how they're measured. So a normal stress is simply a quantity that normalizes the force by the size of the object. So the normal stress sigma equals the applied force divided by the area, and that's the area perpendicular to the applied force. PSI and pascals are the normal units for stress. And I put a some conversion factors here. 1 psi equals 6.89 times 10 to the 3 pascals, or 6.89 times 10 to the minus 3 would be megapascals, or 6.89 times 10 to the minus 6 would be gigapascals. So you'll see stresses in terms of psi, pascals, megapascals, and gigapascals. So this is a simple diagram to show a normal stress. So we have a cylinder, we apply a force to that cylinder, and then the area of the cylinder is A. So simply, the stress equals the force divided by the area. If we apply the force to elongate the cylinder, it's in tension, and that's a positive stress. If we compress the cylinder, it's in compression, and that's a negative stress. So we elongate a cylinder, we put it in tension. Basically, we're pulling the refractory apart. We're stretching or extending the bonds between the atoms. If we compress the cylinder, put it in compression, well, we're probably closing microcracks, but we're also pushing the atoms closer together. So when the refractory is brittle, especially at room temperature, the failure or the fracture is going to occur in the orientation such that the fracture plane is perpendicular to the applied stress. So refractories are weak in tension and relatively strong in compression. So when we have a normal stress, we also have a normal strain. Strain has no dimensions, and it's the change in length divided by the original length. So epsilon is the normal strain. LF is the final length. L0 is the initial length. So LF minus L0 divided by L0 just equals delta L over L0. And again, a strain, because it's a length divided by a length, has no dimensions. So this is just a diagram illustrating the normal strain. So we have a cylinder. The initial length is L0. We apply a force, it elongates. The final length is LF, and LF minus L0 is this distance, delta L. So epsilon equals delta L over L0. That's simply the normal strain. So for Young's elastic modulus, the quantity that appears in most of the thermal shock equations, that's giving you the relationship between the stress and the strain. So sigma is our normal stress, E is Young's elastic modulus, and epsilon is the normal strain. So the modulus relates the stress to the strain, and the modulus is really determined by the strength of the atomic bonds. Since strain is dimensionless, stress and Young's modulus have the same units, either psi or pascals or megapascals or gigapascals. So if you measure the stress strain on a mechanical test machine, if the material is brittle, it's going to be linear elastic. It's going to follow Hooke's law for linear elastic materials. So stress is going to equal Young's modulus times the strain. So a stress strain plot from a mechanical test machine will give you a linear type relationship. And then the slope is the Young's elastic modulus. So at some point during loading, you'll reach the fracture strain, epsilon F, and the fracture stress, sigma F, and failure will take place. So this is a very simple way of measuring Young's modulus, generating a stress strain curve and taking the slope. So I've listed some typical strains to failure. Brittle ceramics such as a refractory material, the strains to failure are very small, 0.01. Metals, the strains to failure are usually greater than 0.1 or even greater than 1. And polymers, the strains to failure are usually much greater than 1. So brittle materials have very small strains to failure. So I mentioned that atomic bonds determine the elastic properties. So this is the atomic basis for Young's elastic modulus. So this equation is for the potential energy, and there's two terms here, an attractive term and a repulsive term. A, B, N, and M are constants, and R is the interatomic separation. So the potential energy equals minus a constant A divided by the interatomic separation R to some power N, plus another term B, a constant divided by the interatomic separation R to the M power. So the first term is the attractive term, attracting the atoms. And when the atoms get too close together, they start repelling. So you have to take that into account with the repulsive term. So if we plot potential energy versus R, the interatomic separation, this first dotted line here is the repulsive term. That's this term here. The second dotted line, and it turns into this solid line, is the attractive term. So the sum of these two is this solid line. That's the potential energy well. So du dr, the slope here, the first derivative is the slope. It equals 0 at the minimum in this potential energy well. So the deeper the well, the stronger the bond, the higher the potential energy, the higher the elastic modulus. So if we take the derivative of this equation, so du dr, that equals the interatomic force F. So the attractive term now becomes N times A divided by R to the N plus 1 plus M times B divided by R to the N plus 1. So the force is plotted here on the bottom curve versus interatomic separation R. So the dotted line is the repulsive term, and then this dotted line is the attractive term. And now this is the force. The solid line is the force versus interatomic separation. So the minimum in this curve corresponds to where this force curve crosses the 0 line here for force. So this is R0, the interatomic separation. The force is 0, and the potential energy is given as the minimum here in this curve. So the Young's elastic modulus is proportional to the slope dfdr, or the second derivative of u with respect to r. So we can draw a line here that's tangent to this curve where the force is 0 at r0. So the slope is dfdr, and it's linear for small displacements. So for a Young's elastic modulus, it's related to the bond strength. So if we look at the U versus R curve, if it has a very deep potential energy well, it's going to have high bond strength, high melting points, low thermal expansion, and a high Young's elastic modulus. And if we look at the force curve, it's going to have a higher slope, dfdr. So the lower the potential energy well, the steeper this slope, the higher the Young's elastic modulus. If the U versus R curve has a shallow potential energy well, the material has low bond strength, low melting points, high thermal expansion, low Young's elastic modulus. And if we look at the slope on the force versus our curve, it's going to have a lower slope. So that's the relationship between Young's elastic modulus, melting points, bond strength, thermal expansion, and so on. So we describe normal stresses and shear stress and normal strains. We have to describe shear stresses and shear strains. So tau equals F over A. Tau is the shear stress, F is the applied force. Now, A is not the area perpendicular to the applied force, it's the area parallel to the applied force. Tau is the same units as sigma, pascals, psi, or megapascals and gigapascals. So this simple diagram illustrates the shear stress. So we have a cube, and on opposite faces of the cube, we apply an equal and opposite force F. And the face of this cube has area A. So now the force is acting on this plane parallel to the force. So tau equals F over A. F is your force, and A is this area. So that's your shear stress. The resulting shear strain is gamma. That equals the tangent of this angle theta. And A and H are geometry-based dimensions. So theta actually equals A over H. But this angle is very small because the strain is very small. So the tangent of A over H can be just approximated by A over H. So gamma is the shear strain. It has no dimensions. And this is the diagram that shows the shear strain. So the solid line is the initial shape of the cube. We apply a shear force. The cube is distorted according to the dotted lines. This is your angle theta. H is the height of the cube, and A is the actual displacement here. So gamma equals tangent of theta, which can be approximated by A over H. So that's your shear strain gamma. So just like we had for Young's elastic modulus, we can relate the stresses and the strains for the shear elastic modulus. So the shear elastic modulus is G. So the shear stress tau equals the shear elastic modulus G times gamma, the shear strain. And G has dimensions of psi or pascals or megapascals or gigapascals, just the same as for E. So if you set up an experiment where you apply a shear stress to a material and measure the shear strain, you get a stress strain plot that looks like this. When it's linear elastic, the slope is the shear modulus G. Ultimately, you'll have failure out of fracture strain gamma F or a fracture stress tau F. And since this is linear elastic, it obeys Hooke's law. So tau equals G gamma. So the third elastic constant we want to talk about that's important for thermal shock is the Poisson's ratio, nu. So nu equals the minus the transverse strain divided by the longitudinal strain. So epsilon transverse divided by epsilon longitudinal. So nu is Poisson's ratio. There's a transverse strain, epsilon transverse, and a longitudinal strain, epsilon longitudinal. Poisson's ratio is dimensionless. It's just a ratio of two strains. And during the Poisson effect, during elastic deformation, the volume under stress remains basically constant. And if we put an X, Y, Z coordinate system on this, and I'll show that on the next diagram, Poisson's ratio can either be equal to minus epsilon Y over epsilon X, or epsilon z over epsilon x. So this diagram illustrates the Poisson's ratio effect. So we start out with a cylinder. It has a radius r0 and a length L0. And we put a x, y, z coordinate system on this. So in the axial direction, that's the x direction. And then perpendicular to this direction are either the z or the y directions. So we apply a force to the cylinder. It elongates, it becomes longer, but then the radius becomes smaller. So we have a final radius RF and a final length LF. So these volumes are basically the same. Since the volume has to remain the same, if we elongate it, the radius has to shrink. So we have a delta L for the change in length and a delta R for the change in the radius. So nu equals, we'll start with this part, minus delta R over R0 divided by delta L over L0. So delta L over R0 is the transverse strain, and delta L over L0 is the longitudinal strain. In terms of the X, Y, Z coordinate system, nu equals the strain in the Y direction, which is perpendicular to the axial direction, divided by the strain in the axial direction, in the X direction. Or it's the strain in the Z direction divided by the strain in the X direction. So these are equivalent since it's an isotropic material. So that's the Poisson's ratio. So these are the three bulk elastic constants for isotropic materials that are important for describing thermal shock, especially Young's modulus E and Poisson's ratio nu. So these are related by this type of equation. Nu equals E over 2G minus 1. So when you're dealing with isotropic materials, if you know any two elastic constants, you can always calculate the third one. There are other elastic constants like bulk modulus, and there are other equations that relate the at least three elastic properties. So once you know two properties, you can always calculate a third. So theoretically, Poisson's ratio has to have a value between 0 and 0.5. So again, brittle ceramics, metals, and polymers. If we look at a brittle ceramic like a refractory, nu is usually greater than 0.1, but usually less than 0.25. So for most refractories, Poisson's ratio is between 0.1 and 0.2. Metals, it's usually greater than 0.25, but less than 0.4. And polymers is usually larger than 0.4. So we're dealing with bulk polycrystalline materials. If it has a low Poisson's ratio, 0.1 to maybe 0.2, that's material that fractures easily and exhibits brittle fracture. If it has a high Poisson's ratio, like a polymer, it tends to flow easily and exhibit plastic deformation. So refractories fall in this group here, and they're quite brittle. So another concept that we have to deal with is stored elastic strain energy. This is the driving force for fracture, whether you have a mechanical strain or a thermal strain. So in the elastic region, the application of stress results in work being performed on the material, and that results in stored elastic strain energy that's stored in the interatomic bonds. So if we start out with again our cylinder of cross-sectional area A and length L0, we apply a force. The new length is LF. The difference is delta L. So the work simply equals the integral from 0 to S times F ds. So F is the applied force, S is the distance over which the force acts, and A is the area perpendicular to the applied force. So our work is defined by this integral from 0 to S, F ds. S is the amount of deflection that's taking place. We can substitute for F sigma times A. We've defined that. We can substitute for sigma, putting in E epsilon. We've also defined that. In this case, the strain is just the deflection S divided by L0. And we pull out the constants. E is a constant. The area is basically a constant. L0, the initial length was a constant. We integrate from 0 to S, S ds. So the work equals the elastic modulus times the area divided by 2 times the initial length L0 times the deflection squared, S squared. We can substitute in for S squared, and that's just L0 squared, epsilon squared. And we just rearrange this equation. E epsilon squared times A L0 divided by 2. A times L0 is the volume. And then we know that sigma is E epsilon. So we can, this term is equivalent to sigma epsilon. So the work is the volume, the unit volume under stress times the stress times the strain divided by 2. So if we divide by V, the unit volume, and call the work per unit volume U, it simply equals 1/2 times the stress times the strain. And you can rewrite this in a couple other forms, 1/2 E epsilon squared or 1/2 sigma squared E. So the work per unit volume, U basically equals 1/2 sigma epsilon. So that's the stored elastic strain energy per unit volume, and it's a function of the stress and strain. Now, the units are a little different here. They're calories per cubic centimeter or joules per cubic meter. So why are we concerned with U? Because it's the driving force for fracture of the brittle materials. This energy, U, is converted into fracture surface energy of the crack. So we go back to our stress strain curve, and 1/2 sigma epsilon is the area of this triangle. So U is simply the area under this stress strain curve. So you can calculate this energy rather quickly from a stress strain curve you get off a mechanical test machine. So if there's a shear stress and a shear strain, it's also 1/2 tau gamma. So that would be the total stored elastic strain energy, taking into account normal stresses and shear stresses. So the stored elastic strain energy is additive. It's the combination of these two stress states. Again, the units are calories per cubic centimeter or joules per cubic meter. So I thought I'd just give a little background information on how you describe the state of stress in a body. And we'll start out with a cube here, an elemental cube, and we'll examine the stresses on the face of the cube. So we'll look at the X face, which is perpendicular to the X axis, the Y face, which is perpendicular to the Y axis, and then the Z face, which is perpendicular to the Z axis. So when you describe a stress, you usually use the Einstein convention. The first subscript is the direction in which the stress is acting, and the second subscript is the plane perpendicular to the axis. So we can look at the first situation here, the x face. So this is the x face. It's perpendicular to the x-axis. So perpendicular to that face is sigma xx. So the normal stress, the first subscript x is in the x direction. The second subscript is the plane, this plane perpendicular to the x-axis. So that's your normal stress. We can look at tau zx. The first subscript is the direction of the stress, and then x is this plane. So the shear stress is in this plane perpendicular to the x-axis. In the first case, the normal stress was perpendicular to that plane. And then tau yx is in the y direction in the plane perpendicular to the x-axis. And on the opposite face in the back here is the back of the cube is the same. And then you can do the same thing for the y faces and then the z faces. So that's the nomenclature for describing the stress state in a body. So when you look at those stresses, it appears there's 9 apparent stresses: sigma xx, sigma yy, and sigma zz, the normal stresses, the 3 normal stresses, and then there's 6 shear stresses. Tau xy, tau yx, tau yz, tau zy, tau xz, and tau zx. It turns out they're equal. So tau ij equals tau ji. So these first 2 are equal, these second 2 are equal, and these third 2 are equal. And I showed that here. So these cancel, and there's really 6 stresses that you have to describe. The 3 normal stresses, and then these 3 shear stresses. And you can put that in a matrix form. The main diagonal has your normal stresses, then the off diagonal is where your shear stresses are. So you can have a stress matrix. You can also have a strain matrix. Your normal strains are along the diagonal, and your shear strains are off the diagonal. So we're dealing with 3-dimensional isotropic bodies for refractories. So here's 3 different kinds of loading situations relating to normal stresses and strains. So this is uniaxial, biaxial, and triaxial. So this would be a simple compression test or a test in tension. So sigma xx is your applied stress. And then the relationships that we just described give you the 3 resulting strains. So there's a epsilon xx in the direction of sigma xx. There's a epsilon yy and an epsilon zz because of the Poisson effect. So you're pulling up this material, let's say in the this x direction, sigma xx, but the material is contracting in the y and z direction. So that's due to the Poisson effect. So that's simple compression or tension loading. If you apply 2 stresses, it's biaxial loading. So you have to, again, count for the Poisson effect. And if you apply 3 stresses, it's the triaxial condition. So you can put this in matrix form: the strain matrix, the elastic constant matrix, and a stress matrix. These are normal stresses and strains. So you simply multiply this first line by this column to get epsilon xx. You multiply the second row by this column to get epsilon yy. And you multiply this row by this column to get epsilon zz. Oops. You can do the same thing for shear stresses and strains. You have a shear strain matrix, a shear stress matrix, and the elastic constants. The main diagonal is where you have the shear elastic modulus G, but there's no Poisson effect in shear, so these off diagonal points are zero. So again, if you take your stress matrix, multiply it by the first line here, you get your shear strain gamma xy. If you take this matrix, this column, multiply it by this row, you get gamma yz. And if you take this column again, multiply it times this row, you get gamma zx. And then you can combine all of that to get the generalized Hooke's law for the isotropic body. So here's your strain matrix, your normal strains, your shear strains. Here's your stress matrix, the normal stresses and the shear stresses. And then here's your elastic constant matrix, where you have Poisson's ratio, Young's elastic modulus, and the shear modulus. So you can take this column, multiply it times the first row, and get epsilon xx, and do the same thing for all the other rows. So depending what stress you apply, or whether there's an actual stress there or at zero, you can get all these different strains based on the elastic properties. So what factors determine the magnitude of the elastic modulus? The size of the cations and anions are important. Refractories are metal oxides, or metal carbides or nitrides. And the valence, the charge on the ions. So if you have a high elastic modulus material, that corresponds to a material with a high bond strength and a high bond density. So to get a high bond strength or bond density, you need small ions. They have to have high valence or high charge, and they have to be dense packed in a crystal structure, small interatomic spacing. So when we talk about refractory materials, there are certain microstructural features that complicate this. You have multiple phases, so the phase distribution is important. You have crystalline phases in refractories, you have glassy phases. The bonding between the phases, the degree of porosity, most refractories have 10 to 25% porosity, unless they're a fused cast material. And the microcracking, most refractories are going to be microcracked to some extent. So especially the porosity and the microcracking are going to decrease the elastic moduli. So if we try to rank the refractory materials with other materials, silicon carbide is a refractory material, silicon nitride is a refractory material, and then our oxides, our metal oxygen combinations, SiO2, Al2O3, MgO, CaO, Cr2O3, and ZrO2. These 6 oxides make up most of the refractory materials in combination with silicon nitride, silicon carbide, and carbon. So going from the bottom to the top, we're going in order of increasing elastic moduli. So silicon carbide is at the top here. Then there's borides, brylides, aluminides, nitrides, the metal oxides, fluorides, chlorides, bromides, and then finally sulfides. So that's where the refractory materials fit in with these other materials. So I have some reference tables here for different types of refractories. So we have a refractory type, Young's elastic modulus, and the shear modulus. And these are you have to multiply these by 10 to the 6 psi. So these are in the millions. So this would be 2 million psi. and then our Poisson's ratio. And in red here, I put structural concrete. This is what your sidewalks or your road would look like. So the E for structural concrete is a little more than 4 million PSI. G is a little less than 2 million PSI, and Poisson's ratio is about 0.1. So an insulating castable has a great deal of porosity, 0.8 million PSI. Fire clay bricks and silica bricks are a little more than 2 million PSI. A pretty dense aluminum castable is close to 6 million PSI. And then materials like silicon carbide and silicon nitride, they're about 60 million PSI. These would be very dense polycrystalline refractories. So these are completely different than these other refractory materials. They're much higher. The G is usually less than half of E, and then Poisson's ratio is pretty much between 0.1 and 0.2, as we would expect. Here's some more examples, refractory types versus just the Young's modulus, and that's again times 10 to the 6 PSI. So we have a fired magnesite, a fired magnesite chrome, and another fired magnesite chrome. So these are higher purity refractories fired at high temperatures. So they're direct bonded. So their elastic modulus is pretty high, 12 million, 9 million, and 12 million. This is another fired chrome magnesite. So the chrome content is higher than the magnesite content. In these other cases, the magnesite content is higher than the chrome. This is material with more impurities fired at a lower temperature. So it's silicate bonded. So it's going to have a lower Young's modulus. Magnesite carbons, there's two here. They're the composites with the carbon matrix, so they're resin bonded. So these two are around 3 and 4 million. This one is another composite with alumina and magnesite, so it's also about 4 million, also resin bonded. Then I have some castables here, a mullite castable, an alumina castable, a zircon castable, and a low cement alumina castable. Now, these are ranging from about 7 to 14, and they're going to be really a function of the particle packing. And if you have the sizing correct and you have very dense monolithic materials, you can have a pretty high elastic modulus. These are our alumina silica refractories. 70% alumina brick that is designed to be micro-cracked for thermal shock resistance. A Super Duty fire brick, 2 alumina castables of 50 and 60%, an alumina brick at 60%, and an alumina castable at 90%, a mullite alumina silica brick, and an 85% alumina brick. So you can see I arrange these in increasing order of E and G. Poisson's ratio is again between 0.1 and 0.2. So I arrange these increasing order to show you that the alumina content has nothing to do with the elastic modulus. This one is highly micro-cracked, so it has a low elastic modulus, about 2 million PSI. This is an 85% alumina brick. It probably has low porosity, a high firing temperature. It's at 13 million PSI. So there's no trend here between castables and fired bricks. It's all going to be a function of porosity and firing temperature and bonding. And this one shows some alumina silica refractories. They're fired refractories. They're not monolithics. So they're going in increasing order of alumina content. And then I show the measured E, the measured G, and the Poisson's ratio. So I'm just showing here that the moduli do not increase with increasing alumina content due to microstructural differences such as porosity levels and microcracking levels. Here's that 85% aluminum refractory at about 13 million PSI. And here's a 70% uh, 70% aluminum refractory with microcracking at 2 million PSI. So normally, if the microstructural features were the same, E and G would increase with aluminum content, but because of the porosity levels and microcracking differences, there's no trend here. And the last one here is for our castable aluminum silica refractories. We have some insulating materials, 50% aluminum castables, 60% aluminum castables, and then 90% aluminum castable. And again, there's no trend here, other than the fact that the insulating materials are going to be low, around 1 million PSI. And this 90% happens to be pretty high, about 8. Here's a 50% alumina that's pretty high, about 6. So there's no distinct trend with increasing alumina content. Again, it's going to be a function of the microstructure, which is, and these castables are going to be strongly dependent on the particle packing, which is controlled by the sizing of the different particles. But if you look at new here, it's always going to be between about 0.1 and 0.2. So these tables show the magnitude of the elastic modulus, the G modulus, and the Poisson's ratio for refractive materials. You can see if you look at all of these tables, 1 million to 10 million is maybe 15 million for E is typical for most refractive materials, unless they're the dense carbides and nitrides, which are going to be much higher. So porosity, microcracking, density, and temperature have a strong effect on the elastic modulus. So if you have a pore in a refractory, the elastic modulus of the pore is 0. So porosity is replacing some of the material. It disrupts the bonding in the material. And pores are also stress concentrators. So when you have stress concentration, you have a more rapid decrease in the elastic moduli, more so than just the presence of pores, which disrupts the bonding continuity. So when you have a pore present, the stress concentration near the pores results in a greater extension, which gives you a lower elastic modulus. So pores redistribute the load to the remaining cross-sectional area because of the stress concentration. That results in a greater extension. So that also lowers the elastic properties. So the approaches for describing the effect of porosity on the elastic modulus are all empirical. So there's a series of empirical equations that have been developed. So very simply, the elastic properties decrease with increasing porosity. So here's an equation for Young's modulus E equals E0. So E0 is the Young's elastic modulus for a material without any porosity. And that's E to the minus B times P. B is a constant in this equation, usually about 4 for most refractory materials. And P is the volume fraction porosity. So as the porosity goes up, this denominator gets bigger and bigger, and E goes down. So if you take the natural log of this equation, you have the log of E equals the log of E0 minus this constant B times the porosity P. So if you plot the log of E versus P, the intercept has to be the log of E0, and the slope is minus B. So the intercept here is ln E0, and the slope is minus B. So if you take a material and you vary the porosity level. You can plot the modulus versus the porosity. You should get a straight line, and the slope is minus b in this equation. And then E0 would be you can get E0 from the intercept. So once you get E0 and P, you can calculate E for any porosity level. So that's one empirical equation. This is another empirical equation showing the moduli decrease with increasing porosity. So in this one, E equals E0. Again, E0 is the elastic modulus for a material without any porosity. 1 minus A times P minus B times P squared. So A and B are constants. P is the volume fraction of porosity again. A and B are given by these constants here. A is usually about 1.9 and B is about 0.19. But really, for each type of refractory that you're examining, you really need to calculate the A's and the B's. So A and B should usually be determined for each class of refractory. And then I think this is the last empirical equation I have showing the effective porosity on the elastic moduli. And this one applies for highly porous materials, insulating materials. So the porosity is usually greater than 70% for this equation to be useful. So E0 again is the elastic modulus for zero porosity, and P is the volume fraction of porosity. So E equals E0, 1 minus P squared. So you can greatly change the Young's elastic modulus by changing the porosity level. And that's really important for controlling thermal shock behavior. Microcracks also decrease the elastic modulus. And the microcrack density is very important for controlling thermal shock behavior. So microcracks can develop during applications where you have thermal fatigue, pre-processes. You can intentionally design a microcrack into a microstructure by controlling the thermal expansion mismatches between the different phases. So refractories are polycrystalline, multiple phases usually. Is usually a glass phase. So those phases will have expansion mismatches. So microcracks are two-dimensional, they're thin cracks. Pores are three-dimensional. So these planar microcracks, there are orientation effects. So if the microcrack is parallel to the normal stress, it has a less effect on the elastic modulus. But if it's perpendicular to the stress, it's going to have a higher effect on the changing the modulus. So microcracks are going to decrease the modulus. And again, controlling the microcrack density is going to be important for controlling the thermal shock behavior. So there's multiple approaches here for describing the effect of microcracks on the elastic properties. So the first one is by Walsh. In this equation, he describes the effect of the microcracks, but he assumes there's no microcrack interactions. None of the microcracks are linking up and forming larger cracks. So the elastic modulus E for a microcrack material equals E0, and that's the Young's elastic modulus if we have a microcrack-free material. And that's times this ratio of two Poissons ratios. Nu is a Poisson ratio for a microcrack material, and nu0 is the Poisson's ratio for a microcrack-free material. So he's describing the effect of microcracks on E by this Poisson's ratio difference here. So nu over nu zero, he defines as 1 minus 4 pi. N is the microcrack density, the microcracks per unit volume, times A. A is 1/2 the average crack length, and A is cubed divided by 3. So you would substitute that ratio into here. It's not easy to measure the microcrack density or the half crack length. Another approach, the second approach here is by Salganic. He accounts for microcrack interactions. So this is the equation he derived. It has E0 for a microcrack-free material, nu zero for a microcrack-free material for Poisson's ratio. Again, it has N, the microcrack density, A, the half average crack length, and he also has the equation for nu here, which includes nu zero, N, and A. So if you solve this equation for Na cubed, you can write an equation for E just in terms of nu zero and nu. The third approach I hear is by Budiansky and O'Connell. Again, they account for a microcrack interaction. So here's another equation for E, and here's the equation for strain. So in this top equation, he has E0 again, nu, and now epsilon for strain, and epsilon is Na cubed, and it's given by this equation, which has nu and nu zero in it. So putting epsilon into this equation, you eliminate Na cubed, so you have Young's modulus again in terms of nu and nu zero. And then the last approach here is by Hasselman and Zing. Again, it counts for microcrack interaction. So this equation has E0, nu zero, again, Na cubed. And then he has an equation for the effect on Poisson's ratio, which includes nu zero and Na cubed again. And you can eliminate Na cubed and get E in terms of the Poisson's ratios, nu and nu zero. So that's the approach for describing actually 4 approaches for describing the effect of microcracks on Young's modulus and Poisson's ratio. So you can plot E over E0, and that goes from, well, in this case, 0.4 to 1. So it's the fraction here, and this fraction, nu over nu zero, goes from 0.5 to 1. So here are the 4 different models: Walsh, Budiansky and O'Connell, Hasselman and Singh, and Zalganic. So they're all pretty close, all showing the same kind of relationship. As the material becomes crack-free, you're going in this positive direction. These ratios become smaller and smaller, and they become 1 at this point. So these are the models describing the effect of microcrack. I don't think anybody has modeled the relationship between porosity and microcracks in one model, but you can calculate the average crack length. You can measure the average pore size. Porosity, when pores are stressed, especially if they're not round pores, they can create more microcracks. So thermal expansion mismatches can create microcracks. Pores can create microcracks. But I don't know of any models that include both pores and microcracks. So if we start out with at room temperature and we're looking at a dense polycrystalline ceramic. The stress strain curves are going to be linear, and typical values of strength might be about 50,000 psi. The strains to failure are going to be low, 0.001. And for dense ceramic materials, E is about 50 million psi. The ratio of E over G is usually about 2.5 to 1. So G is less than half of E. And Poisson's ratios are about 0.2, maybe up to 0.3. So at room temperature, sigma F and E for refractories, because of the high microcrack density and high porosity, is going to be much lower than these values. So if we increase the temperature, maybe to 1,000, 1,200 degrees C, and again, for dense polycrystalline ceramic, the stress strain curves are still going to be linear, but the values of strength are going to decrease maybe 10 to 20%. The Young's modulus is going to decrease 10 to 20%, and Poisson's ratio is going to remain the same. So sigma F and E compared to a polycrystalline ceramic for a refractory is going to be even lower, but they're going to follow the same trends where they decrease 10 to 20%. So if you plot Young's elastic modulus versus temperature, so this is E from 0 to about 15 million psi versus temperature from about 0 to 1,100 degrees C. This is a 60% MgO matte chrome brick. This is a 70% alumina low cement castable, 70% alumina brick, a Super Duty brick, a 50% alumina castable containing carbon, and an insulating castable. So these are all decreasing 10 to 20% in this temperature range. So that's pretty typical of how the modulus will vary with temperature. So if you go to temperatures greater than 1,000 or 1,200 degrees C for a dense polycrystalline ceramic, now these stress strain curves are becoming nonlinear. That's because there's some plastic deformation taking place, maybe some creep taking place. So strength falls off rapidly, the elastic modulus falls off rapidly, but Poisson's ratio is still going to be about the same, 0.2 to about 0.3. So strength and modulus for a refractory material is going to decrease more rapidly and at lower temperatures than for polycrystalline ceramics. So we can plot Young's modulus versus temperature, and MOR, which is modulus of rupture or bend bar strength, again versus temperature. So the solid line is the Young's modulus, and that's for a dense polycrystalline ceramic. We're going from 0 to about 40 million psi. So you see the strength, the modulus decrease 10 to 20% until you reach a point around 1,200 for this material. There's a Nina curve and a rapid decrease in the Young's modulus. The dotted line is for the strength curve, which goes from about 0 to 40,000 psi. So there's a slight increase in the strength due to stress relief, followed by this rapid decrease where it becomes plastic. So refractory materials follow the same kind of behavior, but the modulus values are going to be lower, the strength values are going to be lower. So we can plot the stress versus strain. This is in PSI, and the strain goes from 0 to about 0.002. And the circles indicate where fracture takes place. So for a polycrystalline ceramic, we're looking at 20 degrees, 40 degrees, 400 degrees, 800 degrees, and 1,200 degrees C. They're still pretty linear. when you get to higher temperatures like 1250, 1300, 1325, 1350, and 1375, you can see they're bending over, they're becoming nonlinear. So you get a Young's modulus off of these linear curves very easily. But when these bend over, you usually take the tangent at the origin here to these curves to get a tangent modulus. So you can see the slopes are decreasing, the modulus is drastically decreasing. So here are two plots for modulus versus temperature for refractories. And this is Young's modulus in kilograms per millimeter squared. This is in PSI times 10 to the sixth. And this is again Young's modulus in kilograms per millimeter squared, and that's times 10 to the 3. I always think in PSI, for me, it's easier. Here's degrees F, and here's degrees C. These are 4 fired refractory materials, two direct bonded MgO materials, and 2 high alumina refractories. So 3 of these are exhibiting a strength increase due to stress relief. This one doesn't have any stress relief, but when they hit temperatures around 2000 degrees F, you can see the rapid decrease in Young's elastic modulus. And these are unfired castables, a vibration cast material, a gun material, a low cement castable, and 2 alumina based castables, 45 and 70% alumina. These are start out as unfired, so when they're heated up, the hydraulic bond is destroyed, the porosity increases. So these are all going to be showing a decrease in the Young's elastic modulus. This temperature here, 1000, 1200 degrees C, is a little bit low, lower than where the ceramic bond due to sintering is going to start taking place. So these values will eventually increase as these materials are sintered at higher temperatures. So I think I'll stop there. The beginning of next class, we'll go over the different ways you can measure the elastic properties, dynamic resonance technique, a velocity of sound technique, and the static technique. So I'll finish this up on Thursday, and then we'll continue on with some of the other thermal properties. So thanks for attending today. Have a good rest of your day, and I'll see you on Thursday. And again, if you have any questions that you think about, you can always email me or give me a call. My contact information was in the initial emails and on the also on the website describing these courses. So again, thanks, and have a good rest of your day.
Thank you.
Thanks.
Thank you.